and now we're recording, and there's, see the sound, so I'll just, what's that?
Is the mic turned on?
Yeah. Yeah. Testing 1, 2. It's good enough, right? Okay, why don't we get started here? I'll just very briefly introduce Dwight Wendschlag, and he'll tell you a little bit more about himself. But Dwight is a graduate from UND. He earned a master's degree here in mechanical engineering, and I think you had a job before Amoco.
I did.
It was auto industry?
Yep.
And you worked in the auto industry. That's part of the story I'm a little fuzzy about. But you then worked at Amoco in the upstream part of the business as a reservoir engineer, and later at BP after the merger. And what he's agreed to do is come and talk with us about his perspective of the engineering challenges and opportunities in upstream business from his perspective. And so Dwight is also a member of our industry advisory board. So for the petroleum engineers, you'll if you're coming to the meeting on Friday, you'll see Dwight. And so let's just welcome Dwight and turn it over to him.
Thank you. Thanks, Scott. So I know we had a few more walk in since we had our last survey. So how many in here are not petroleum engineering students? Okay, so we got about half a dozen. Okay, so just a little bit more about myself. I actually graduated from UND with a bachelor's degree in mechanical engineering, and then I went to work for Ford Motor Company for a couple of years. But when I graduated, I knew I wanted to go back to graduate school. Wasn't exact. I knew I wanted to go back to engineering graduate school, but I wasn't sure exactly what. Worked a couple of years, did come back. At the time, I kind of had my head wrapped around the idea of biomedical engineering, which was kind of in its infancy at that time. But the mid-'70s, which is when this, early to mid-'70s, was kind of the energy crisis time, the first energy crisis in this country. And there was a lot of focus on energy, and we had a couple of new professors in the ME department at the time who were very focused and enthusiastic and persuasive. And so I ended up in looking at storing heat in porous media, in groundwater aquifers. And that got me then in a different direction, so into a petroleum engineering direction. So what I want to do is share with you today a little bit about from my perspective, how I see my ME background kind of supporting the PE world, but it's going to be obviously slanted from my eyes because I'm the only one who had that, my experience. And I was, given that it's a relatively small crowd, what we'll do is if you have a burning question during the presentation, raise your hand. If it's something short, we'll probably address it right there. If it's something that I think might take a little longer, I'll just ask you to hold on to it till the end because we do want to kind of manage time. I don't want to have people hanging here any longer than you have to be because I know it's a busy time of year. It's a busy time, it's at the end of the day, end of the semester. It's been a long time since I experienced that, but I remember it well. So with that, we'll start. So I'm from western North Dakota. I grew up in a little town called Powers Lake, North Dakota, which some of you may know. It's a little bit north and west of Stanley. And at the time, it was kind of the end of the, in the middle of the first North Dakota oil boom, which isn't anything like the boom of today, but it was a boom nonetheless. And my knowledge of the oil and gas industry at that time could pretty well be summed up in these two pictures. I knew that if you saw one of those, a well was drilling. Didn't really know any more than that. And I knew if you saw one of those, there was an oil well there. But I really didn't think too much about what went on below this level. And I didn't think too much about what went on below the stuffing box here. And I certainly didn't think about the fact that there was probably a lot of technology and engineering associated with getting oil out of the ground and into my gasoline tank in my car at the time. I did, when I was in high school, kind of fairly early on decided that engineering was the path I wanted to pursue, and mechanical engineering actually, but I certainly didn't think about the petroleum industry at the time as a place to practice that craft. So what I hope to share with you today is a little bit of how I've come to appreciate that there is a lot of technology in the oil and gas business, and a lot of engineering challenges, and we're going to cover those kind of at a high level. And those of you who are PEs, some of this you're going to say, "Oh, ho hum, I already knew that," but hopefully I can put a little different spin on it and put a little detail, given that I've been doing it for close to 40 years. So what we're going to do, the first thing I'm going to do is make a differentiation between upstream and downstream. We're going to be talking about upstream, and again, many of you maybe know what that means, but it's one of the risks you always run when you talk about to multiple disciplines is you get locked into a jargon. Every discipline, every craft has its own jargon, and so please, if I say some jargon or use an acronym that you don't know, I try to avoid that, but sometimes I slip. Call me on that right away. We're going to talk just a little bit about history, just because it's kind of fun. And then I'm going to work my way through what I call the challenges from the bottom up. So from the subsurface to the wells, and then the surface. Then I'm going to talk a little bit about costs and risks and why it is so important to have a good grounding in the technology of this business. Some what I'll call technical workforce challenges, which are, I think, particularly apropos to the people in this room. And then say a few things about, well, with all this focus on alternative energy sources and climate change and all this stuff, is this a dead industry? I mean, what you guys are at the front end of something, and you'd like to know it's going to be around for a while. So I'll just share a little bit of information about that. Oops, went the wrong way. Okay, so first upstream, downstream. Upstream is the exploration and production of oil and gas. So it's what happens below the surface. The downstream is refining, transportation, marketing, and the petrochemical industry. So refineries, that's downstream stuff. What goes on with wells and from those wells into the surface facilities is upstream stuff. And usually that transfer between upstream and downstream takes place at what we call the sales meter. So when that barrel of crude goes through a sales meter and gets counted towards that producer's barrel, at that point it's handed off to the downstream industry. Now, some companies are strictly upstream industries. Many of the companies that operate in western North Dakota are strictly upstream industries. They're exploration production only. The other side of that is the Exxons and Shells of the world, who are multi-stream, and they have all facets. But we're going to be talking about the upstream. That's where I spent virtually all of my career. Oops, I keep going the wrong way. Okay, first a little history. So, you may not think about it, but oil has been used in North America for about 600 years. It was used by the Native Americans for salve, mosquito repellent, as a purge, as a tonic, and 150 years ago it was used to grease the wagon wheels on the wagon trains that were heading west across the United States. That oil was produced from seeps, and seeps happen all over the world. I've read not too long ago that there's an estimate that there's about 1 million barrels a day of barrels of oil equivalent of oil and gas seeping throughout the world. Most of it, probably the majority, is actually under the ocean, but that's a lot of seeps. But within the continental U.S., there was, what's now the continental U.S., Pennsylvania was a place where there was a lot of seeps. Wyoming had a lot of seeps, and they were easy to find. You didn't have to do any seismic work or anything like that. You could see them, and they were relatively easy to produce. The typical way to produce them was to build a little bit of a dike or something, or if they were seeping into a stream or a pond, you'd skim it off. And you did have some of the same environmental issues you have today, contaminated groundwater and surface water. And typically, you might get 6 to 10 gallons a day or a quarter of a barrel. So easy to find, easy to produce, not a lot of volume. And we would call that, I would think, a low-tech operation. Not a lot of engineering went into producing seeps. Now, in 1859, Colonel Edwin Drake drilled a well in Titusville, Pennsylvania. Contrary to what some people believe, I was not around to observe the drilling of that well. That well was 70 feet deep. It was drilled at 3 feet a day. It took almost a month. And the first day, once they finally hit the oil-bearing zone, it made 25 barrels. So it was considered a rousing success relative to the quarter of a barrel or so you could get from skimming seeps. So a little higher tech. Edwin Drake managed to get financing for this thing, and there was a lot of impatience after about the first couple of weeks, but he managed to convince his investors, keep the faith, we're going to make this work, and we've got a technology here that's going to be able to drill this well, and that technology was a cable tool drilling rig. Who in here knows what a cable tool drilling rig is? Okay. So for those of you who don't, how many of you in here are familiar with a clamshell digger that you dig a post hole with? Okay. Cable tool rig is kind of like that, not exactly because you can't open and close, but it literally is drilling by going down, and it's got a kind of a nose on it that picks up some stuff and picks it up. It's not very fast, not very efficient, but it did the job. And until about the mid-1920s, all the oil wells in the United States were drilled with a cable tool rig. So today, this is what we're going to be focusing on, is today. We drill in very remote environments. Deserts, mountains, tundra with permafrost, deep water. Scott didn't mention, but I retired from Amoco BP in 2002. I took a couple years break, and I went to work for a company called Cobalt International Energy in Houston, and their focus was strictly deep water off Gulf of Mexico and off of West Africa. The water depths in excess of 5,000 feet. So very, very remote environments. Wells, 35,000 feet deep, some of the deepest ones now. 2-mile horizontal wells, as those of you who are familiar with the Bakken well know. Multi-stage fracs that have enabled the shales in the Bakken to flow. In some cases, drilling rates exceed 1,000 feet per day, a little better than Colonel Drake's rate. Individual wells. Now, there aren't lots of wells that make 50,000 barrels a day, but there have been some that exceed 50,000 barrels a day. That's a boomer. Facilities are placed in very remote locations on the seabed in several thousand feet of water on floating platforms. And so the oil industry has evolved to be a very high-tech operation. In fact, in the deep water environment, you'll hear people say that landing somebody on the moon is actually, from a technological standpoint, easier than drilling and developing a field in 5,000 plus feet of water. So, kind of the bottom line is continuing advancements in the development and application of technology have been what's made the oil industry and gas industry what it is today. And that's why sitting where you are is with a potential future in the oil and gas business is pretty exciting, because the way technology is developed and applied in the oil industry today is rather extraordinary. And as an engineer, that should be pretty exciting, because I'm going to guess that everybody in here that's an engineer, you're in here because you like to solve problems. And I can tell you, this is an industry that will present you with some amazing problems to solve. Okay, so let's start with from the bottom up. Subsurface challenges. The first challenge is we're engineering what we cannot see. When I worked for Ford, if I was working on a part for an engine, which I was in their engine division, or I was doing some testing or whatever, I could open the hood, I could see the part that I was involved in designing, I could see it work. If it didn't work properly, I could see it fail. If it did work properly, I could see it work well and be happy to see that. But as a reservoir engineer or an engineer working the subsurface, you don't ever see what you're engineering. It's also a very sparse data environment, particularly early on in the exploration and appraisal stages. you might be looking at a prospective field the size of the city of Grand Forks, and what you have to work with is a hole that big. That's all the data you got, and from that you're asked to extrapolate what does the rest of the city look like. So if you drilled a well in the middle of UND and hit the power plant, and that's all you knew, your first inclination to say, well, the whole city looks like UND's power plant. It doesn't. But at that point, you've got investors and managers pounding on you to say, well, tell me what it looks like. Certainly, you've got a well now. So what you do have is a few squiggly lines on a piece of paper called a well log. If you're really lucky, you've got a core, which is, so in many cases, your first data is only those squiggly lines on a piece of paper. But if you're fortunate, in some cases, wells are cored, and that's actually drilling with a barrel that can retrieve rock from the subsurface. So at that point, you actually have an opportunity to look at it and do measurements on it and correlate that with the squiggly lines you have. But you're still looking at one small piece of rock in a very large area. And in fact, a guy I used to work with years ago, his favorite saying was, you're basing everything you know on the one piece of rock that's no longer there. Because you've got that up on the surface, and you're assuming the rest of the reservoir looks like that. But given that, even in spite of that sparse data environment and the limited amount you have to work with, you've got some pretty big decisions to make. Are you going to develop or not? If you are, how are you going to develop it? And then once you do develop it, what's that performance going to look like? What kind of rates are we going to make? What kind of reserves are we going to get? And the picture does become clearer with time. As you drill more wells, you get more data. As you produce, you get more data. And the real irony is, the only time you really know the most about the field is the day you abandon it, because every piece of information you get adds to the puzzle. And this might be 10 years, might be 20 years, might be 50 years. First field I worked on in central Wyoming at the time was 80 years old. That was 40 years ago. That field is still producing. It's 120 years old. So they still don't know what the ultimate recovery from the Salt Creek field in Wyoming is. So part of the challenge is, how do you, with limited data, make billion-dollar decisions that in some cases can make or break a company if it's a little company? And I'm not going to sit here and answer all that, but I'm just going to put this out as a challenge. Part of your challenge as a reservoir engineer or an engineer in the petroleum business is to say, with this limited amount of information, how can we put a picture together with a range of statistical uncertainty that's meaningful in order to make a decision that is more likely to succeed than fail. And Scott and I have had years of doing that, and to be perfectly honest, you do sometimes fail, but hopefully you succeed more than you fail. And that's no different than any other discipline, quite frankly. The other challenge that's under the subsurface is the fluid. Now, the petroleum engineers know this well, but the fluid is in a porous media. It's not in a tank. And I used to think that a well was literally drilled into a tank. I mean, not a metal tank, but that there was this big void underground that when you drilled a well, whether it was a water well, oil well, whatever, you just tupping into a tank and you float it out. I can tell you, because there were surveys done years ago, a lot of people think that a gasoline pump is actually over the same kind of thing, but we're not going to go there. So let's just, for the sake of argument, assume that the volume of that barrel is a cubic foot. And the surface area of the inside of that barrel, and please none of you check my math, but I think this is close, it's about 4.8 square feet. So that means the barrel will hold about 8 gallons of liquid, and if you open that spigot, essentially all of it will flow out. So we can recover 100%. That's a recovery factor of 100%. Now, unfortunately, that's not what we have to work with. What we have to work with is a porous media. Porous media is a network of grains and pores that have pore throat sizes and channels that are in the micron sizes. So your fluid doesn't get to flow out of that nice big barrel. It flows through these little tortuous paths and has to get through micron-size pore throats. Now, let's assume again that barrel is a cubic foot, but it's filled with porous rock. Typical porous rock will have a porosity or a void space of 10 to, at the high end, maybe 30%. So, for the sake of but the surface area of that porous rock is about the size of a football field. It's no longer 4.8 square feet. If you were to take all this stuff and iron it all out, it's almost the size of a football field. The barrel will, if we assume about 25% porosity, holds about 1.5 gallons, and if the spigot's open, only about 3/8 of a gallon, or 25% of it, will flow out. Due to surface tension, capillary forces, and a number of other effects, that fluid wants to stay in there. A lot of it is bound to the rock. And one of the biggest challenges you have as an engineer is to figure out how to free that stuff that's bound. Because if you can only get 25% in many fields, that's not enough. Now, I can tell you, that's called primary recovery, by the way. And in the Bakken, that number is probably more like 10 because of the structure of the Bakken. If the spigot, and so we're going to get 25%. Now, let's say that we just pour some water in the top. Now, water and oil don't mix. We know that. But it will form a bank, and it'll push some oil down. So if you do that, you might get another 25%. You might pick up a little more of that oil that's coming through here. That's called water flooding, by the way, in a field scale. And so between the two of them, you get about 50%. Now, the vast majority of the oil fields in the world, that's kind of where the recovery stops. So 50% is not a bad number. Sometimes you can get 60, sometimes it's 35, depending on the circumstances. But you can go one step further, and you can flush it with a solvent. So if you can flush it with a solvent, you might get another 15 to 20%. So you can maybe get 65 to 70%. You're still leaving 30% in the ground. And so when you hear about challenges to get an incremental recovery, there's still anywhere between 30 and 50% of the oil that you've already found that you haven't got, but you know where it is. Exploration is it's a very high-risk operation because you're drilling wells in often remote areas, high-risk areas, and you may or may not have a discovery. Here, you know where this oil is. It's right underneath your feet, but you haven't got it all. You've left 50% there, or in the case of a tertiary project, maybe only 30. But it's a lot of oil. There's billions of barrels of discovered oil in the world that have not yet been recovered because we haven't unlocked that remaining 30%. It's a big challenge, and it's one that's being worked on a lot. We don't have any chemies here, do we? But that's where chemical engineers really play a big role. Now, to add one further deal, I was using this barrel with the spigot on the bottom. In actuality, in our case, the spigot's on the top. We've got to bring all this stuff up. So it just adds one more element of challenge. Now, our next challenge, reservoir fluids. When most people think of crude oil, this is kind of what they think of. Some black, nasty stuff that flows out of flows viscous, flows out of a drum like that. Actually, reservoir fluids hydrocarbon fluids are very complex. They have multiple phases and lots of changes in phase behavior with changing conditions. It's not all black, nasty stuff. These are all crude oils, and in fact, I worked a field in western Wyoming where there would be one more bottle here that was almost crystal clear. Crude oil. They range anywhere from gravities for light stuff. So we're talking about densities. So densities that maybe we 0.7 specific gravity all the way up to almost 1, 0.95 or so, and viscosities ranging anywhere from half a centipoise to on upwards to thousands of centipoise in some cases. The big challenge is that they're multi-phase. At a minimum, you're likely to get oil and gas, and ultimately almost all fields produce water. So now you've got 3 phases flowing, all competing for that same pore space that I described earlier, and the sum of the parts is not equal to the whole. When these multiple phases compete for pore space, you might have your total effective flow capacity is about half of what it is if it's a single phase flowing. So that's one of the big differences between hydrocarbon production and a groundwater aquifer. A groundwater aquifer is a single phase fluid. It stays single phase almost all the time unless you're in a really hot thermal area. But for the most part, it's a single phase fluid. And for me, when I did my graduate work was on groundwater aquifer, and this was a real eye-opener to find out that things didn't flow in a hydrocarbon environment like they do in an water environment. The other thing I mentioned, your temperature and pressure is constantly changing as you're producing. So for those of you who, in your chemistry classes, thought you'd never like to see another phase diagram again, if you're working with hydrocarbon fluids, you learn to live and love phase diagrams, because most of the time you're kind of in a fairly constant pressure regime, but you're not in a constant pressure regime. And so you're moving through that phase envelope as you're producing. And the ability to get effective production, economic production, is dependent a lot on your ability to predict that phase behavior over time with changes in pressure and temperature. The other thing about the fluids is they can be nasty stuff. Some of them are deadly. They have hydrogen sulfide. It's actually not that uncommon. Hydrogen sulfide is a very deadly gas. It's fatal in just a handful of parts per million. Carbon dioxide is even more prevalent. It's generally not fatal, but it causes some pretty serious problems for development. The fluids are corrosive. They have minerals in them as well, which contribute to scale. They can have heavians and waxes and asphaltenes. This is a couple of examples. This is an example of scale from a fluid that had either calcium carbonate or barium sulfate in it. And this 6 inches or so that you had is now about 1 inch in diameter. This is pitting and corrosion, likely from hydrogen embrittlement due to hydrogen sulfide. Those are problems that happen all the time. And it's a mechanical engineering challenge, it's a chemical engineering challenge, and it's a petroleum engineering challenge to figure out what materials do we need to use to prevent that from happening in the case of pitting, or in the case of scale. What chemicals? There's some chemicals we can put in that will help us mitigate that or eliminate it, keep it from happening. It's always easier to keep stuff from happening than it is to fix it later. The next thing is it's a tough environment. I already mentioned some harsh conditions. I think if you talk to some of the drillers who come up here from Louisiana, they would say the Williston Basin might be on that list of harsh conditions in the middle of January. But they do work. You do work in some harsh conditions. I mentioned extreme depths. The Gulf of Mexico has some wells that exceed 35,000 feet. Massive rigs, 2.5 million pound hook loads. And in a second, I'll show you why you need that. The other thing is extreme pressures. When I first started work for Cobalt, the geologists and geophysicists were working up some prospects in the deepwater Gulf that were very deep. I had a little bit of information to go on, and I predicted that this one prospect would have bottom hole pressures approaching 26,000, 27,000 psi, which it's just outrageously high. And they drilled that well about a year after I left Cobalt. I left Cobalt in the middle of 2012, re-retired, as it were. And fortunately for them, it was a discovery with a 26,000 psi bottom hole pressure. That's extreme pressure. You need heavy wall pipe and wellheads to deal with that kind of stuff. This is an example of a rig. That one I think that's a 2 million pound hook load rig on a floating vessel. And now the reason you need that is, we'll talk about wells a little bit later, but if you're going to be running casing, 30,000 feet of casing, that casing string weighs close to 2 million pounds. So if you don't have a rig with those kind of capacities, you you can't lift that casing. You can't control it going in, and you certainly can't lift it coming out. This is a stacking cap. Now, I'm sure most of you, well, maybe you remember the BP oil spill of about 5 years ago. And they finally put a cap on it, and for that well flowed for 87 days. And there was a lot of pressure, a lot of press. People saying, well, why don't they just put a cap on it? How hard can that be, right? That's a stacking cap. That's the kind of cap that you have to use to cap a well like that. That thing weighs, I believe, 180 tons. Every oil company that does work in the deep water now has to have access to one of those. There are a couple of companies that each have a couple. So that if there is another incident like the BP oil spill, you could get a cap deployed on site. So when you're talking about wells, and that well, by the way, had a bottom hole pressure of about 13,000 psi, not 26, but the wall thickness on the materials in that cap is about like that. So for those of you who like machining, if you go to FMC or a company that makes that kind of stuff, it kind of takes milling to a whole different level, because those are machined. They're big, they've got inner bores, that big around, wall thicknesses like this, and they're machined to, thousandths of an inch tolerance, because in some cases they're metal-to-metal seal or an O-ring seal. And so it's a manufacturing process challenge extraordinaire. The wellbore itself, as I said, is a challenge. This is a typical wellbore. Yes, William?
How expensive are those caps? A couple $1 million?
About $3.5 to $4 million, which is about the same. Your question is timely. I'll come to that, because that's a subsea tree, which is about the same. This is a wellbore for a typical deep water well. This one that doesn't happen to be deep. It's only about 5,800 meters. But you're telescoped down, and this one has a 30-inch, a more common size for the really deep wells is 36-inch. So you're starting out with a bit that's that big around, where the first hole is normally jetted in, and then you're running concentric casing as you go down. And it's this long string, this one right here, that can weigh upwards of 2 million pounds. Because to hold that pressure, that wall thickness is, it's an inch wall thickness. Now, that's a typical onshore. The wellhead controls on a well are called a Christmas tree. I think there's probably some good historical reason for that, but I don't know what it is, and I'm not going to make something up. I've been known to do that, but I won't today. This is a subsea tree. This is a tree that would sit on a well that's completed on the seabed. That tree also has to be able to withstand the intense pressures of a 25,000 psi bottom hole pressure. So it's machined with the kind of tolerances I talked about earlier. Those can range from $3 to $5 million each. Drilling that well to 35,000 feet costs about $250 million. So, other wellbore challenges. One is the size. Yes?
Okay, so when you drill, this is a question about the offshore rig. So when sort of an offshore rig drills your offshore well, and when it's completed and done and everything, is the rig still there? And
No.
it turns into a production rig, or where does all the production go?
No, the rig is not still there. The rig is strictly for drilling, and it drills these wells. And if in what's called a wet tree completion, and I'll have a picture of that a little bit later, which might make it a little more clear. But the wells are drilled, the rig moves off, and then a different production facility is set on. And actually, if you hold that question again, I've actually got some pictures of deep water production facilities and subsea completions, which I think will. So, in terms of the wells themselves, they're relatively small diameter, and so when you have a well that's like a Bakken well is 10,000 feet vertical, 2 miles, another 10,000 feet horizontal. You're working in that. You can be 2 to 4 miles away from where you have to have stuff going on in a very small diameter, and The tools that do that are at one time simple and one time very sophisticated. You know, if you can't really get too exotic with what you do 4 miles away in a hole that big. But on the other hand, you have to be able to do a lot. You have to be able to gather data. You have to be able to, in some cases, clean up wells. You have to be able to put in production facilities and stuff in those wells. And all of that is done in wells that are in well bores that are anywhere from 4 to, in some cases, 7, 8, 9, 10 inches in diameter, but still not very big, relatively speaking. By the way, even heavy wall pipe that thick, 35,000 feet long, you can bend like a horseshoe. Materials. So for those of you who are into metallurgy, and I will have to confess that when my mechanical engineering classes, metallurgy was my least favorite. Some of it was the material, a lot of it was the professor. He's long gone, so I can say that now. But metallurgy is a huge deal. There are a lot of materials, different kinds of materials. You know, stainless steel, well, there's many kinds of stainless steel, as you probably know. And so you have to have materials that are strong, they're corrosion resistant, they're flexible, and to the extent you can control the weight, you want to keep that weight down as much as possible because you've got to be able to lift this stuff in and out of the hole. The other thing is they may need to last 50 years or more. You know, like I said, there are some fields that are in excess of 80 to 90 years. And you have to be able to get tools in them. So the size, type of materials, accessibility, big challenges, and you know that engineers are best equipped to deal with. That's an example of some pipe that you would run in a well with a 25 to 26,000 pound bottom hole pressure. That's about an inch wall thickness. That's heavy stuff. When they haul that stuff at 40-foot lengths, you can haul 3 of those on a truck because that's all the weight you can carry. So how to drill and complete? Wellbore trajectory. You know, up until probably 30 years ago, virtually all wells were, for the most part, vertical. You know, they did wander a little bit, but they weren't extreme angles. At probably 25 to 30 years ago, you started to see what are called high-angle wells that were drilled at maybe 15, 30, even 45 degrees. Today, of course, you got horizontal wells that are not only long, but they're tightly controlled. You know, the advent of electronics and GPS and monitoring well drilling, it has enabled that. Stimulation, probably a word that doesn't mean much to some of you, may mean something to those of you who've had some experience in the oil business. But wells typically, when they're completed, you know, you run pipe to the bottom, then you shoot holes in that pipe, and some wells will just start flowing. You usually have a negative pressure on the backside, and the wells will just burst in and start flowing. A lot of them do not. A lot of them require you to go down in there and do some kind of stimulation, something to open up those holes or to even clean up that formation. And typical ways to do that are acid or hydraulic fracture in the case of the Bakken. But you know, the Bakken formation and the multi-stage fracs is relatively new technology. But fracturing as a technology has been around since about 1952, 53. So you know, people talk about fracking now like it's something brand new. It's not. It's been used. There's been tens of thousands of wells in the world fracked, and yes, there have been one or two or a few that you know maybe have come up the backside, but there aren't any that have burst through the formation and come up like it's often depicted in documentaries and advertisements. Then you've got a question about will this well have enough energy to flow naturally, or do I need to put in artificial lift? I'll say a little bit more about that in a second. And for deep water, you got the question of subsea completions or production platform completions. So I will address your question when I talk about that. So this is a horizontal well, or a depiction of a horizontal well with a multi-stage frac. This is a deep water development subsea completion. So what you have is a floating vessel that is a production facility, and I've got some other pictures of production facilities later. But you actually complete these wells on the seabed. And as you can see, this seabed is not all in one big flat surface. In fact, some of the seabeds are really very, very rugged. So what you have here is you have wells that are drilled, and then you've got these trees that I talked about on the wells, and then you have subsea flow lines that run to what are called risers up to that production facility. And those risers, I mean those flow lines can be as long as 10 miles. You typically don't like them that long. There's too much friction loss, but it can be that long. Risers are, from the mud line to the top, so 5,000, 6,000. The deepest subsea wells are about almost 10,000 feet of water offshore Brazil. So all of this stuff is done down on the seabed, and by ROVs. I've got a picture of one of those in a little bit too. Say more about that. Artificial lift. As I said, when I was growing up, we saw a lot of these all over. I didn't really think too much about what was underneath that stuffing box. But as it turns out, one of the first jobs I had in my tenure with Amoco was working on what were called problem wells, beam lift wells that failed. Best experience I had. I was working with 2 field guys. We spent 3 to 4 days a week in the field getting data on wells that had frequent rod parts and pump failures. These are relatively simple pumps. I don't know exactly the history, where the invention of the rod pump came about, but I have heard one story that it actually is from the Chinese, and they actually, the pumps were made out of bamboo, and they were used, in shallow wells to pump water. But they're a simple device, but because of all of the problems I mentioned earlier with the complex fluids and some of the other scale and other things that you can produce, these little ball and teeth things can fail a lot. And so choosing the right material for that, choosing the stroke length and the speed and all that, those are not simple. As it turns out, they're not simple. It turns out that those are relatively complex engineering calculations. And so what I thought was a pretty simple device, and what looks pretty simple actually has a pretty good piece of engineering behind it. Artificial lift can also be done with electric submersible pump or an ESP. These are literally downhole pumps that have a motor and a pump, and you run an electrical cable on the outside. That poses problems of its own because that electrical cable has got to be able to withstand the same corrosion and all the other nasty environment that everything else has, and they don't necessarily always like that. And these are high voltage. Those are usually 1,000 to 1,500 horsepower motors, and because they got to fit in a hole that big, you got to have enough windings to get that much horsepower. They're long, so the pump might be 80 feet long. That poses some interesting challenges too, because you can't. While you can put tubing around a bend, a pump and a motor doesn't like to go around a bend very well. So you have some different ways you have to play with that. And I won't mention much about gas lift. It's just another way to, if you pump gas down, sometimes you can lighten the fluid and cause it to float up. Some of the problems once you get into production, your perforations can plug. You can have mechanical failure, scale and corrosion, we already talked about. Sand production or material production, solid material production. As you might expect, when this fluid comes in, it'll often want to wash sand with it or some of the reservoir with it. And your mechanical parts don't like that. Many of these parts are very tight fitting, and when you put a little sand in there, you're either going to wear the part very rapidly or in some cases stick it completely. Wellbore failure, not uncommon. Sometimes they collapse. Oftentimes they can leak. When they do, they got to be fixed. If you're in the middle of western North Dakota, you move a service unit on that thing and fix it. I don't know what the current service units rates are in western North Dakota, but it might be, I don't know, $10,000, $15,000, $20,000 a day. If you're in the middle of the Gulf of Mexico or offshore North Sea or in the deep water where you've got one of these subsea completions, you've got to move a rig over that costs $1 million a day. So you got to be fairly judicious in how many times you can do that. And then in many cases, ultimately, almost all oil fields eventually start producing water, or gas fields as well. And being able to manage and handle that water can be a big challenge. Because at the end of the day, you're paid on what you flow, on the oil you flow through the meter, not the water, not anything else. And as soon as you start losing production, managers come and find you. So, facilities. We've talked about the reservoir, we've talked about the wellbore, now we'll talk about facilities. You know, these fluids, I've mentioned the complexities there, but once they get to the surface, they're very volatile and they're very flammable. We know all the time. In fact, driving over here, I don't know if you've heard this, but another train derailed near Harvey, 10 cars, fire. The fire was still burning, no injuries, fortunately. But these fluids are very flammable, very volatile. They're multi-phase. I mean, they're multi-phase in the reservoir that causes problems in the porous media, but pumps and flow lines don't like multi-phase flow either. And so you end up with complex flow regimes, even in a simple pipe. And, and being able to predict the flow regimes with time, with temperature and pressure, is a significant challenge, because how you design those flow lines and facilities is really very dependent on your ability to predict what's going to happen. When am I going to have multi-phase flow? Because ultimately you'll probably almost always get it. And how am I going to deal with it? And sometimes it requires sizing lines much bigger than you think you should need. Very high velocities in these pipes, especially when you have wells that are that make 20, 30,000 barrels a day. High flow rates, large vessels with high pressure requirements. Here's an example of an onshore facility. That pressure vessel, these are separator vessels where the fluids come in, multi-phase fluids, and due to residence time in that vessel, the gravity will segregate out oil and gas or water if there's water there. But those vessels are often 1,000 psi. Sometimes your primary separator is 1,000 psi. Those vessels can be large, 30, 40 feet long, 10 to 15 feet in diameter. So you think about a vessel that's 20 feet long, 15 feet in diameter, that has to hold 1,000 psi. There's a lot of square inches in that vessel, and so that vessel has got to be designed to be able to hold that pressure for years, 40, 50 years. Flow assurance. That's a fancy oil field term that talks about what making sure that your lines stay open and that things can keep flowing, even under shutdown conditions, etc. You have very large rotating equipment. So this is mechanical engineer's dream here. Big compressors, big pumps, in some cases big generators, gas turbine generators. I worked in western Wyoming that used reciprocating pumps that took in the gas at about 1,000 psi and discharged it at about 8. Piston sizes were like a locomotive. They're that big around, that long. I don't think 4 of us could have lifted a connecting rod. They're massive things. Turned about 500 RPM. Ran so smooth you couldn't hear them. You could stand on the floor next to them, you didn't feel a thing. That's good engineering. And then I've already mentioned remote locations. So, offshore facilities challenges. You've got all the stuff I mentioned before, except now you've got a space problem, because you don't have several acres on which to put your stuff. You've got a floating vessel that might look like one of those up there. So, and you've got to get all this large equipment I talked about in some pretty tight quarters. You've got living quarters on there. If you're going to have people living on something, they got to be safe. You got to keep them comfortable. One thing the oil business learned very early: you got to keep them well fed, because you can get two things that workers are going to demand in a remote location: good food and satellite TV. If those 2 requirements are met, you can get by with a lot of stuff. These are often remote. Sometimes they're 150 miles offshore. You got to resupply. You've got long transit times to get workers back and forth. You've got long transit times to get supply back and forth. It's a logistical challenge extraordinaire, and there are people who are just gurus at it. I have great admiration for them. Then you got to worry about how you're going to get that fluid off into the meter. You export it. Assembly can be a challenge. Think about putting something on a floating vessel, The way these are typically built is the bottom part, what's called the jacket, is built first. It's towed out, it's anchored or moored, and then the top sides are brought out on a barge, and they have to be lifted onto that floating jacket. So you got a lot of stuff going on because the water's going like this, it's going like this, and you've got usually 2 barges, heavy lift barges, because that surface facility might weigh, probably 80, 100 tons. You got to have a coordinated lift, and you've got to lift it up and move it over the jacket and set it down. A few years ago, Texaco had spent about $1.5 billion on a facility. They were setting their surface facilities on the jacket. One of the cables snapped. That facility is now sitting on the bottom of about 5,000 feet of water. You just start over. You can't retrieve it. You aren't going to lift it. You got weather issues. The Gulf of Mexico, you got hurricanes. In the North Sea, you got 100-foot seas. And those platforms are designed to be out there producing through all that stuff. Flow assurance, huge problem because, as I mentioned, if you're going to fix things when you're offshore, it costs 10 times as much. So here's some examples of some facilities. This is a grounded facility, so that facility you could actually drill wells from. That might have a drilling rig on, so the wells, so you could drill and produce in the same facility. Most of the time you don't do that. It's more like the one up on the right. That's a floating, it's called an FPSO, floating production storage and offloading. And you can see it's subsea completions, and then everything runs to that vessel. It looks like a ship, but it's actually anchored in place. It's moored with mooring lines that are about that big around. This is just another example of the floating facility. And that's an ROV, a remote operated vehicle. So everybody who thinks they were squandering and wasting their time playing video games in their youth, this is the salvation, because those things are operated remotely by joysticks by guys and women who are extraordinary at what they can do. I am never failed to be impressed by the things that they can do with those things. In the BP spill, early on they thought they could close the rams by replacing a hydraulic line. They actually were operating a 3/8 inch open-end wrench to unscrew the hydraulic line with one of those. So, and it's moving. I mean, it's impressive. Costs and risks. To drill and complete a Bakken well, I think, is about $7 to $10 million. It's coming down all the time. As the learning curve goes up, the costs come down. Probably coming down more now that the price of oil is down. Deepwater exploration well can cost $150 to $200 million. Those are expendable wells. You drill them, make a discovery, you cap them, and you go walk away, because they're not drilled, they're not designed in such a way to be a production well. A deepwater development well might cost $300 million by the time you get the right jewelry in there. Deepwater facilities, $2 billion to $10 billion. Operating costs, $5 to $25 a barrel. So managing costs is a big deal. Managing revenue is one thing we've been talking about a lot, about what you do to keep production up, but managing costs is a huge deal too. Risks. Safety, number one. All of the things I've talked about, volatile fluids, flammable fluids, corrosion, H2S, all that stuff. The petroleum business is a risk business in terms of safety. And so there's no way you can put too much emphasis on safety. And most safety personnel I've worked with are engineers, because they understand what goes on beneath just the surface. And I'm not talking about the surface of the ground or the water now. I'm talking about the surface of the technology. Environmental risks, resource estimates. This is how reservoir engineers either make or break their credibility. Product prices. I think we're witnessing some of that right now. A year ago at this time, oil was $100 a barrel. Now it's about 60. It was down to 45 a little while back. Political risks if you're operating, particularly in overseas environments, but even in the U.S., regulations change all the time. And when you develop a field or come up with a development plan based on a certain set of regulations, and then they change about the time you're ready to implement, you've got to have the design flexibility to be able to respond to that. And then in foreign governments, it has to do a lot with tax changes and their take and stuff. And then workforce skills, which kind of gets me to where I wanted to be with respect to a couple things on environmental. So this is a Bakken well, and I'm sure many of you have seen these pictures. You know, when these wells are completed, they're typically flaring gas for a period of time. The state allows gas to be flared for a period of time. At the end of the day, you wouldn't like to be flaring any. You know, it's just not a good deal. Number one, you're putting stuff into the atmosphere that doesn't belong there. Number two, you're wasting resources. If I'm the mineral owner underneath that and my royalty is based on total revenue from that well, I don't want that gas going up in flames. I want it showing up in my check. So figuring out what to do with that gas before you have a line to hook it to, big deal. And I know there's a lot of emphasis on that. I've seen some of the stuff in the engineering magazines that come out and stuff from UND. And I know the state is very conscientious about getting on top of that. Safety, that's what happens when safety is not managed properly or when bad decisions are made. 12 people lost their lives on that. In 1988, there was a production facility in the North Sea called Piper Alpha went down. 169 lives, I believe, were lost on that. When things go wrong, they can go very wrong. And that is not what you want to be involved with. Okay, let's talk about workforce challenges. I think I got one slide after this one. First thing is solid foundation. And by that I mean, you know, you've got to have a good grounding in the technologies in your discipline. And can't overemphasize that enough. You know, too often, and I can recall taking stuff and saying, am I ever really going to use that? I mean, it looks good in a textbook, but am I ever going to really use that? You know, I keep my textbooks available, and I refer to them often, even after 40 years, because and having the foundation allows me to know what textbook to go to and what part of the index to find the question. If you don't have the solid foundation, sometimes you don't even know that you need to ask the question. That foundation is critical, and the time you spend here agonizing over what professors are doing to you, most of them have a method to their madness, and if you can walk away feeling like you got a solid foundation, that's really important. Getting the hands dirty. You know, I did some recruiting for a number of years. One of the things I've seen over the years progression in terms of engineering disciplines, all disciplines, is that we get engineers who can really work the computer, but they've never had their hands dirty. And some of the more elite universities are the biggest culprits of this. It's great to be able to run simulators and be able to manipulate software and input and output, but until you really understand, until you've put your hand on a polish rod to feel the pound fluid below, or until you've heard the gearbox on a pumping unit, or until you've actually sat in a logging truck and watched logs being run, you really can't appreciate that input and output that you're doing with that computer. An attitude of continuous learning. I probably learned as much in the last 6 years as I did in the first 30. And I'm still learning today. And I'd learn it, like I said, I keep my textbooks on my shelf. I refer to them. I have other resources. There's a massive amount of publication of papers in the oil business. Some of the problems that we think that we're trying to solve today were actually solved in 1940. We just don't think to go back and look at them. And so that attitude of continuous learning is important. Last bullet is probably the most important one as far as I'm concerned. Upstream engineering in the upstream business is a team sport. It's the integration of many engineering disciplines. It's not a PE game. It's PEs, MEs, chemis, electricals, civils in some cases. It's all disciplines. Working closely with the geoscientists, geologists, geophysicists, paleontologists, biostratigraphers, all of these fancy geoscience names, but at some point you've got to be able to bridge the gap, at least to understand and develop a common language. Very, very important. Close interaction with operating personnel. At the end of the day, they're the ones who make the money. You can do all the fancy design work you want in an office, but it's those people out in the field that make you the money. And then unless they trust you and want to work with you and you can communicate with them, that relationship can be a little sticky. So the technical skills are critical, but I get asked often, you know, what should the curriculum focus on? And I think communication and interpersonal skills can be absolutely as important as anything else. And so it's kind of a three-legged stool. It's communication, interpersonal skills, solid foundation, and then kind of with gaps filled in by getting your hands dirty and continuous learning. Okay, the last thing I wanted to talk about is this where you want to do your work? Is this where you want to go? Is this a dying industry? This actually came out of the February 2015 issue of the Bakken magazine. It's from the annual energy report of the Energy and Information Administration, their May 2014 report. 2012, oil and gas made up about, 65%, 37 for oil, 28 for natural gas. 65% of the energy usage, worldwide energy, or U.S. energy usage, I'm sorry. In 2040, the projection is that yes, while some of the alternative energy sources are going to come up a little, oil is still 32 and natural gas is 30, 62%. So unless a completely revolutionary energy source comes along, windmills are not going to replace 62% or 65% of our energy usage. This was a good industry to get into. When I got into it 40 years ago, it's a great industry to get into today. So it's a bright future for people who like problems, like challenges, like to work well with others, and at the end of the day, feel like you're contributing to something meaningful, like supplying light and heat. I've said many times when people say, geez, you're kind of in an industry that's got a bad rap. How do you feel about that? And I say, well, if we had never invented the iPhone, we'd probably be okay. Might be a little traumatic, but we'd probably be okay. But if we didn't have energy, we'd have a problem. So I will never apologize for spending 40 years in this industry. So I don't know. We've kind of eaten up an hour. I've got a little more time. If somebody has any questions, yes.
You being a mechanical engineer, what got you interested in the oil and gas industry?
When I was in grad school, I was a TA, and I actually taught the senior ME lab for 2 semesters. And 2 of the guys that were in that lab, 2 of my students, had summer experiences in that case both of them for Amoco, one in a field office in Farmington, New Mexico, one in a field office in Oklahoma City. And they came, and they were just effusive about what great experience they had. And so when Amoco came on campus, I interviewed them, and I was impressed. And the other thing is, I'm from North Dakota. I had spent 2 years working in Detroit. I don't know if anybody in here is from Detroit, but it's not exactly the best place in the world to live. I was given the opportunity to go work in Wyoming. That seemed like a lot better deal. And so, but it really was 2 students and their summer experience who got me to take a look. And as a result of that, I talked to Amoco, I talked to Texaco, I pretty much talked to all energy companies. I only talked to a few. And once I shop like a man, not like a woman. Pardon me. But when I find something I like, I buy it. I don't keep shopping. And after I got the offer from Amoco, I took it. So I quit interviewing. But that was it. Sorry if I offended anybody back there, but my wife won't take me shopping. I hinder her style. All right. Any other questions? Yeah, back here.
So earlier when you were talking about the offshore technology, do you see hydraulic fracturing taking place on offshore rigs? Do you see sort of a lot of the onshore enhanced oil recovery techniques being carried over to the offshore sector?
Well, fracturing is done in offshore today, but there are limits to what you can do. You're talking about pressures, extreme pressures. So, when you get down to where you've got pressures in excess of 10, 12,000 psi, it's very difficult to have enough surface horsepower to break the formation. And horizontal drilling is also used offshore, but once you get below about 17,000, 18,000 feet, you get a lot of incremental torque when you make that horizontal leg. And so right now, I think the limit is probably about 18,000 feet to drill a horizontal well offshore. But that technology will continue to grow, and so will the frac. But there is kind of a finite limit to how big you can make your pumps. When you get to these extreme pressures, and quite frankly, when you get to these extreme pressures, if you can put enough back pressure on, you don't need to frac. I mean, those wells flow. 20, 30, 40,000 barrels a day. But there's always ways to apply some of the technologies, and that's one of the things the industry was really kind of bad about for a long time is not deploying technology developed one place another. And I think the industry in general has gotten way better at sharing information, and the internet and those things have actually facilitated that. William, you had a question as well.
Yeah, do you believe living in North Dakota or the Midwest in general has benefited your work ethic or compared to other workers around the industry?
This is going to be a highly biased answer, but yes. I said I recruited a lot, and I'll tell you, I was recruiting a guy one time. I was at South Dakota Tech, and virtually all of the engineers I recruited on their resumes had some summer experience of some kind. He didn't have any, and I was kind of impressed with him. Was kind of low key, but he just you just get a gut feel. And I said, "What did you do during your summers? Were you going to school? What were you doing?" And he says, I worked on my dad's ranch, so I didn't put that on there." I said, "Put it on there. Because my experience is that people from this background have got a work ethic and a common sense farms and ranches and getting nuts and bolts stuff done that makes them intensely valuable to any industry." And I would take a graduate from the University of North Dakota, Montana Tech, South Dakota Tech, over a Stanford grad any day. Does that answer your question? Yes?
What do you think, I know it's kind of hard to say, but what do you think is going to happen with oil in the recent years with like oil prices and stuff, and what do you think is going to happen with western North Dakota and oil in general?
Well, if I could predict oil prices very well, I would be a very wealthy man. But I can share with you kind of what I see in the industry, things that I read, and some of the colleagues I talk with. I don't think anybody is expecting a return to $100 oil for a while. And by that I mean maybe till into 2016 or even beyond. I also don't think that, excuse me, I don't think we're going to sit at nominally $50 for a long time either. The best guess is maybe by the end of the year it might be back up in the 70s and 80s. Now, the reason for that is, the OPEC still has a big influence on the world oil price because they have the biggest percentage of the production. But many of those countries, while they can produce oil at $25 a barrel, drill and produce oil at $25 a barrel, their whole country infrastructure is based on oil revenue. So for the Saudis, for example, to support their country infrastructure, not their oil field infrastructure, their country infrastructure, they need $90 to $95 oil. Now they're able to tolerate the current price because they've got billions and billions of dollars of cash reserve. They're probably in the best shape. Russia needs about $105 a barrel to support theirs. Venezuela needs about $120. And so the question is, who's going to cry uncle first? And because at some point, not all the countries have cash reserves like the Saudis. So I think it's unrealistic to think it's going to stay at 50 to 60 for a long time. But let's say it does. What does that mean for western North Dakota? This was also, I think I read this in a previous issue of the Bakken, but the sweet spot in the Bakken, which is kind of Montreal County and the area around Parshall in that area, they can break even at about $30. So they're going to continue to drill, even with the current price. The fringe stuff needs about 70 because those wells, they only come on at about 200 barrels a day, and they decline about 80% a year. That's a typical shale well. So that's what all of the rig, I think North Dakota's only got about 50-ish rigs running now. It was 190 a year ago. All of those rigs that aren't running are the ones that we're drilling out in the fringes of the basin. But there will continue to be drilling in the sweet spot, even at the current price. And for the wells that are already drilled, the break-even's about $15. So if you got a well down and it's already pumping, as long as you're getting more than 15, you're making money. You may not be recovering your drilling costs, but at least you have a positive cash flow. So does that answer your question?
Yeah.
I mean, and the other thing is the Bakken isn't going away. That's a massive reserve, and I think it's very realistic to expect the drilling to go on there for 20-plus years. Because even drilled and completed as they are, those wells are not draining very much. They're not draining that they're drilled on. So there will be infill drilling for decades. Any other questions? Yes.
The professional groups or societies you maintain memberships in?
I still am a member of the Society of Petroleum Engineers. I wouldn't call myself an active member. When you become a member of any of the societies, you're assigned a chapter. Well, Montana, the only chapter is in Billings, and I live in Whitefish Kalispell area, so I'm a few hundred miles away. So I don't regularly attend meetings, but I do stay plugged in to them. They've got some great learning stuff, and quite frankly, if you're a member, you pay for your membership many times over if you access many papers, and I do access a lot of papers. I was an ASME member while I was working for Ford, but once I got in the oil business, I dropped that. I am a registered professional engineer in Wyoming and Colorado, but I haven't maintained that in active status either, but I was registered at one time. Any other questions? I know it's getting late. Yes, one more.
So earlier we were talking about how the ultimate recovery rates for Bakken wells is at 10%, and I remember hearing earlier that when they were first drilling and fracking out in Williston, that recovery rates were at about 2%.
Right.
And that's a huge increase. Do you see bigger increases in ultimate recovery, or do you think it's going to level off pretty soon? Or
I think it's knowing what I do about shales, I think it's unrealistic to expect you're going to get up in the 15-20% range. But going from 2 to 3, which it was initially, as you said, to up to nominally 10 is pretty significant. And the leap that made that happen was extending the laterals from 1 mile to 2, and then going from kind of nominally 30 stages to 40 stages on the fracs. Could you drill 3 miles and get and frac 50 stages? Probably at some point, but that will add more oil and won't necessarily improve your recovery factor. So what I know, and the other thing is I don't foresee, and I could be really wrong here, but I don't foresee water flooding the Bakken. I just can't envision how you could do that. I know a lot about secondary, tertiary recovery, and I can tell you Bakken is a primary depletion play. So the way you improve the recovery in a primary depletion play is well bores. And that's why I can say with some conviction that they'll be drilling 20 to 30 years out there. Okay? Yes?
That's a bold question. What's incremental torque?
Well, the rigs, are there any drilling engineers in here? Drilling people? So the way rigs work, they're rotary rigs, and so you're turning at the top, and all that pipe down is rotating down the bottom. Now, if you're in a nice vertical hole, spinning this is fairly easy, even if you're in rock. But once you make a bend, and you're still rotating, that pipe is still rotating, your torque has gone up dramatically. So the incremental torque is the torque between drilling that vertical section and what it takes once you've gone around the bend. And that gets to be really hard when you get very deep. Does that make sense? Okay. I've successfully exhausted everybody. Well, thanks so much. Like I said, I know you guys and girls are busy. I know you're toward the end of the semester, and you've got lots of stuff to do, but I really appreciate you taking the time to come, and hopefully it was worth your time. So thanks so much. Good. Was that all right?
Yeah.
You need to pause something? Or
So what I'll do is I'll stop recording,